Albert Einstein's proposal of the theory of relativity in the early 20th century radically altered how we conceptualize the relationships between space, time, and gravity. There are two parts to this theory, and they are special relativity and general relativity. Subscribe to Science Arena for more engaging scientific content, and don't forget to like and comment on this post to join the conversation. Albert Einstein's proposal of special relativity in 1905 was a revolutionary idea that radically altered our perception of the cosmos. It claims that all observers moving at constant relative speeds experience the same physical rules. This means that as long as your speed remains constant, the fundamental principles that control the behavior of the universe remain the same for you. Our common-sense conception of how the world functions is shaken by this premise. In general, we hold the view that everyone, regardless of their velocity, should be subject to the same physical laws. However, special relativity as explained by Einstein demonstrates that this is not the case. It reveals a world in which the laws of physics are not fixed but change depending on the position and velocity of the viewer. Let's look at an example to see if it helps. Picture two people, one on the station platform and the other aboard the train. Both observers should, in principle, record the same speed for a moving item, in accordance with classical physics. But special relativity reveals that this is not the case. Assuming the train is running at a steady speed, an on-board observer will get the same reading for the speed of the passing object as an on-ground observer. A bystander to the tracks, however, will get a different reading on the speed of the moving object. Special relativity causes this discrepancy in measurements. According to special relativity, weird events emerge as an object approaches the speed of light. As we move forwards, it appears that both time and space are expanding. Therefore, time passes more slowly for a fast-moving observer than for a stationary one. The effects of length contraction and time slowing have been empirically confirmed, and they are profound. They reveal that our everyday perceptions are restricted to a narrow range of velocities, which challenges our intuitive concepts of time and space. While these have a small impact at normal velocities, they become more noticeable as we approach the speed of light. The special relativity theory relies heavily on the fact that the speed of light remains constant. According to Einstein's theory, the speed of light in a vacuum is constant for all observers. This indicates that the speed of light will always be measured to be constant regardless of how quickly an observer is moving. A fundamental implication of this theory is that space and time are not discrete but rather intertwined, resulting in a four-dimensional fabric known as spacetime. The shortening of distances is an intriguing effect of special relativity. An object's length in the direction of motion is said to appear to shorten or contract when moving at high speeds relative to a stationary observer. This occurrence contradicts our common-sense view of the universe, in which objects retain their fixed dimensions independent of their velocity. This surprising prediction of special relativity has, however, been repeatedly confirmed by experiments. Let's think about a hypothetical situation to better understand this idea. Imagine a spaceship with a measuring rod attached to its side moving at speeds approaching the speed of light. When looking at the speeding spaceship from a stationary observer's point of view, strange things begin to occur. When the rod is at rest, the viewer will see it as shorter than it actually is. According to special relativity, the reason for this shortening of length is because space and time are intrinsically linked. Both space and time become warped as an object travels across space-time at near light speeds. For a moving object, the passage of time and the apparent size of space in the direction of motion both slow down as the speed of the object increases. The degree to which an object's length is shrunk by moving away from an observer is determined by the relative velocity of the object and the observer. The degree of contraction rises with the object's speed. However, at typical speeds, we do not detect any significant variations in the apparent lengths of objects due to these effects. Several methods have been used experimentally to confirm the shortening of length, such as the Large Hadron Collider, LHC, which accelerates up subatomic particles to near light speed. Scientists have proven the phenomena of length contraction by comparing the sizes of these particles while they are at rest and when they are traveling at high velocities. Cosmic rays, which are high-energy particles from space, provide additional proof. These particles produce secondary particles that decay in microseconds when they collide with Earth's atmosphere. However, because of their high velocities, they travel shorter distances before decaying than would be expected if length contraction did not take place. These results corroborate the predictions of special relativity, demonstrating that length contraction is an intrinsic property of our universe. This phenomena is critical in resolving the discrepancy between the laws of physics and the reality of motion at high speeds. but it also poses challenges to our ordinary perception of space. Understanding the universe more intimately is made possible by special relativity's acceptance of length contraction. It serves as a timely reminder that, in order to gain a complete understanding of the cosmos, we must go beyond our limited, intuitive understanding of space and the behavior of objects. Don't doubt the apparent length of a fast-moving object until you consider the amazing revelations of special relativity. It serves as a timely reminder that our conception of space is not static, but rather a result of the ever-evolving interplay between time, motion, and the laws of nature. In 1915, Albert Einstein incorporated the effects of gravity into his innovative theory of relativity, resulting in the theory of general relativity. Our common-sense conception of gravity as a driving force between material bodies is shaken to its foundations by general relativity. Instead, it posits that the existence of mass and energy curves the fabric of space and time, giving rise to gravity. Planets, stars, and galaxies, and other huge objects, warp spacetime due to their mass and gravity, as explained by general relativity. Imagine that these items make a dent or a curve in the otherwise flat fabric of spacetime to get a sense of the warping impact they have. A greater mass causes a more noticeable bending effect. Smaller celestial bodies and even particles near the big object will take different courses due to the localized warping of spacetime. Rather than being dragged or drawn by a force, these things just follow the inherent arcs in spacetime produced by the enormous object. Imagine a huge piece of rubber laid out flat to represent this idea. Now, put a heavy ball in the middle of the sheet so that it presses down on the rubber and makes a depression. If you roll a lighter ball next to a heavier one, the lighter ball will follow the heavier ball's line of curvature. Similarly, in general relativity, objects' paths through spacetime are set by the curvature of spacetime due to mass and energy. This newfound knowledge of gravity has far-reaching consequences. It explains why smaller objects, such as planets orbiting stars, move in elliptical routes rather than straight lines when close to such enormous masses. This also explains why starlight curves around the sun during an eclipse, or any other time its proximity to a huge object causes it to bend. General relativity has been widely tested through observations and experiments, and has proven to be extraordinarily successful in explaining a wide range of gravitational events. Einstein's theory was given substantial support and elevated to the rank of a momentous scientific discovery by the confirmation of the bending of starlight during a solar eclipse in 1919. The implications of general relativity's view of gravity as the curvature of spacetime extend well beyond what can be seen with the naked eye. It has far-reaching consequences for our comprehension of the universe at all scales. General relativity provides a comprehensive framework that combines gravity with the fabric of spacetime, explaining phenomena as diverse as planetary motion, the behavior of black holes, and the expansion of the universe. General relativity challenges our naive conceptions of the cosmos by showing that gravity is not a force operating at a distance but rather a result of the curvature of spacetime. It provides a radical revision to our concept of gravity by exposing it as an essential part of the structure upon which our world rests. Think about the amazing revelations of general relativity the next time you question what holds you to the ground or contemplate the vastness of the universe. It serves as a timely reminder that gravity is not a force acting upon us, but rather the sculpting of spacetime by the presence of mass and energy. Numerous experiments and observations have proven general relativity to be correct. Sir Arthur Eddington's observation of the bending of starlight around the Sun during a total solar eclipse in 1919 was one of the most important confirmations, showing that Einstein's predictions were correct. The theory of relativity has had far-reaching consequences, and it is still molding how we view the cosmos. This theory helps us understand the underlying nature of reality, from time dilation to the curvature of spacetime. With that, we complete our examination of relativity theory. Come back with us as we explore other intriguing scientific issues.